Why are we still cleaning pipelines like it's 1995? Seriously, we talk about Industry 4.0, data-driven processes, and highly automated production systems. But when it comes to CIP, many facilities still use almost the exact same cleaning cycles they used 20 or 30 years ago. Long water flushes, high chemical consumption, high energy use, and most importantly, long drawn-out downtimes. And that's despite the fact that water, energy, and wastewater disposal have become major cost factors today. Does CIP work? Absolutely, but is it technically optimized? That's exactly what we're going to look at now, based on actual data. And one quick disclaimer before we begin: all data shown here comes either from published studies or documented industrial applications. But one thing is important: every CIP process is ultimately product specific, which means every system design must be individually validated. And just briefly for context, CIP, or clean in place, is usually an automated process used to clean production systems without disassembly. Today, this is the standard across industries, whether in food, beverage, or pharmaceutical production. And the process is basically the same almost everywhere. First, water pre-rinse, then an alkaline cleaning cycle, followed by an intermediate rinse with water, then an acid cycle, and finally a last rinse with water. The actual cleaning performance is always based on 4 factors: mechanical force, chemistry, temperature, and time. And these are exactly the 4 factors we need to examine if we want to understand where optimization potentials still exist today. If you look at the last few years, you can actually see 3 major areas where optimization has taken place. First, process control. Second, chemistry and temperature. And third, media recovery. So let's start with mechanics and flow behavior. There's an interesting study published in the Journal of Food Engineering in 2017. The study examined how much increased turbulence helps remove fouling, specifically milk fouling. And honestly, the results were quite sobering. Even when flow velocity was increased significantly, from a Reynolds number of around 20,000 up to 100,000, the cleaning performance during pre-rinsing improved by only 10%. So in simple terms, more pump power delivers far less improvement than expected. And in practice, this often leads to the following situation. If the required cleaning performance can't be achieved through more mechanical force, companies simply extend the rinsing time. And that has direct consequences: higher water consumption, higher energy use, and longer downtime. The study also shows that higher temperatures, at least in the pre-rinse, have hardly any additional effect above about 45 degrees. The technical conclusion is therefore quite clear. Mechanics and temperature help, but with strongly diminishing returns. Once mechanics and temperature reach their limits, chemistry becomes the only remaining lever. And this is where real progress has been made. In this field, studies show, for example, that enzymatic cleaning at about 50 degrees can deliver similar results to classic alkaline acid cleaning at around 80 degrees. That's up to 30 degrees less and a correspondingly lower energy demand. Another approach is so-called single-phase detergents, where several cleaning steps are combined and intermediate rinsing phases can be eliminated. So real efficiency improvements have definitely been made here. But, and this is important, based on our experience, many companies still continue to rely on the classic process. The trend is more about extending chemical usability and reducing losses, not necessarily about completely redesigning the system itself. The third major area is product recovery. This is where technologies like ultra and nanofiltration come into play, allowing CIP solutions to be treated and reused. Studies show recovery rates of around 75%, while still achieving very high cleaning performance, over 99% for certain substances. Even regenerated caustic soda can provide cleaning performance comparable to fresh solutions. So this represents a measurable reduction in resource consumption. In practice, however, many partners tell us that chemicals are already commonly recirculated, replenished, and regularly treated depending on the application. So once again, evolution rather than revolution. So if we summarize all of this, process control has improved, chemical use has become more efficient, and resources are partly reused. But the mechanical cleaning itself, especially during water rinsing, still basically works the same way: high volume, continuous flow. And this is exactly where physical limitation exists. Because the wall shear stress inside the pipeline, the factor that actually determines cleaning performance, does increase with turbulence, but not indefinitely. At some point, pump capacity, pressure, and system geometry create clear physical limits. And in practice, this often leads to either longer rinsing times or increased chemical use. And this is exactly where the complex process comes in. Instead of continuous water flow, the system works with targeted air-water impulses. And the effect behind this is crucial. These air impulses accelerate small water volumes to velocities of up to 20 meters per second. This creates local wall shear stresses up to 100 times higher than with conventional continuous flow. So what does that mean in practice? The level of fouling is significantly reduced before chemicals are even applied. And that means less chemistry is required and total process time is reduced. From comparable cleaning applications, we already know reductions of up to 80% in cleaning time and up to 96% lower water consumption. That may sound hard to believe, but with Comprex, it is absolutely achievable. Validation for direct application within CIP processes is currently underway, together with the Fraunhofer Institute. We expect results by mid-2026. The system can also be retrofitted into existing production environments without changing the entire process setup. If you look at the development of recent years, CIP has mainly become more efficient in three areas: process control, chemistry, and media recovery. Mechanical cleaning itself, however, has remained largely unchanged. And that is probably where the greatest remaining savings potential still exists today. If you want to find out what savings potential exists within your CIP process, simply send us your product along with a short description of your current rinsing step. We'll test your product first with your current process and then with Comprex under identical conditions. You will receive a direct comparison, a written report, and full video documentation. And the test is completely free of charge. And now I'd really like to hear your opinion. Where do you currently see the biggest optimization potential in CIP? Data, chemistry, recirculation, or mechanical cleaning? Feel free to share your thoughts in the comments.